So in the last video, we talked about making carbon-carbon bonds by deprotonating the alpha carbon of a carbonyl compound, making it into a nucleophile, which then attacks an electrophile to make a new carbon-carbon bond. So just to revisit that real quickly, if I take this compound up here, I treat it with potassium terbutoxide. Remember that this generates the thermodynamic enolate. In this case, we only have one alpha carbon to worry about, so it's not such a big deal. And then this enolate attacks the partially positive carbon, and we make a new carbon-carbon bond. And so in this case, I'm just going to write pH for phenyl. We draw out all the carbons that were here in the first place, and then our alpha carbon right here makes a new bond to this carbon right here. And so we add those two to that alpha carbon. Remember to count your carbons, disregarding the phenyl group over here represented by pH. We have 1, 2, 3, 4, 5, 6. We have 1, 2, 3, 4, 5, 6. And so we have all of our carbons accounted for. And so this would be our final product. In similar sense, we can treat the same compound with the same base, so potassium terbutoxide. And we can do halogenation of alpha carbon. So instead of making a carbon-carbon bond, like in this case, we would make a carbon halogen bond. I use Br2 here, so we would make a carbon-bromine bond. The final product, again, I'm going to use pH to represent phenyl. And then we draw back out the carbons that were here in our starting material, and then we add a bromine to this alpha carbon. And so our final product for this reaction would be shown here. Notice that for both of these, if you go back to the previous video, look at the mechanism for this, and then we go through the mechanism for this, they are the exact same. So when we are under basic conditions like we are in both of these cases, both mechanisms initially go through a proton transfer elementary step followed by an SN2 elementary step. So if we go through the mechanism of halogenation of alpha carbons, we identify the carbonyl, we identify the alpha carbon, and we see that there is a proton on there that we can pull off. So I'm going to draw that proton out here. Our base is potassium terbutoxide. So draw that out here. And this is going to, like I just said, do a proton transfer initially, giving us our carb anion, which we draw out like this. And then remember that this has a resonance structure, so we want to draw that out. If we push those down, push these electrons up onto the oxygen, we get what we refer to as our enolate, shown here. And so once we have deprotonated using our base, we can then go in and attack one of our bromines. So draw out Br2 here. This acts as an electrophile. We've generated a nucleophile. Now we do an SN2 type reaction where we attack the bromide and kick off a leaving group. And this results in our final product as shown up here. Remember, don't forget your carbons. So we have these two methyl groups coming off the side, and then we've added a bromine to the alpha carbon. Again, don't forget to count your carbons. We have, besides the phenyl group, we have 1, 2, 3, 4, 1, 2, 3, 4, and then we've added our bromine. So you might be asking yourself, why is Br2 or molecular bromine electrophilic when bromine's connected to bromine? They both have the same electronegativity, and so you may think that it's not very reactive. But actually, Br2 is a source of Br+, Cl2 is a source of Cl+, and I2 is a source of I+. So remember, just like sodium hydroxide, sodium doesn't mean anything. All we need is hydroxide, but I can't go buy a bottle of that. I have to buy a bottle of sodium hydroxide. Same case here, I can't buy a bottle of Br+, I have to buy a bottle of Br2 to use in my reaction. You might remember from very early on in the semester I mentioned this, and that's because bromine, chlorine, and iodine, so halogens, are highly polarizable. What does that mean? When an electron-rich species, so like an enolate, remember enolates are nucleophiles, so they're electron-rich, as it approaches the halogen molecule, the electrons on one of the halogens is repelled towards the other halogen, therefore making the one that is being approached by the nucleophile electron poor, and therefore being an electrophile. So just keep in mind that when we use Br2, Cl2, I2, these equal Br+, Cl+, and I+. So I'm going to try and depict what I mean by them being highly polarizable. So down here I've drawn my enolate. Notice I drew it in the enolate form and not as the carb anion. This is the most stable resonance structure, even though it reacts on the carbon and not the oxygen. This blue circle up here around the bromine represents the electron cloud, and so I've tried to show that they are evenly distributed between the two atoms. And then let's see what happens as our electron-rich species approaches the bromine. So now our enolate's moved a little bit closer. It's gone from here to here. And we see that our electrons are not evenly distributed about this bromine. Remember, electrons are negatively charged. Our nucleophile is negatively charged, and so they want to repel each other. And so as this approaches this electron cloud, the electrons move over towards one side, starting to make one of these bromines partially positive. And so now that our enolate has gotten right next to our molecular bromine, essentially all of the electron density has been shifted over towards one bromine, making this one electron rich and this one electron poor. And so since this one has a partial positive charge, it can act as our electrophile, where our nucleophile comes in and attacks. So in the previous examples, we only had one alpha hydrogen, but one thing to keep in mind is that under basic conditions, so we're using sodium hydroxide, potassium terpetoxide, LDA, any type of base, polyhalogenation is going to occur. And so that means that every single alpha hydrogen is going to be replaced by a halogen. So in the earlier example, I drew this molecule up here. We look at the alpha carbons. This alpha carbon doesn't have any hydrogens, and this alpha carbon only has one hydrogen. And so this one hydrogen gets replaced with our halogen that we are using. To give us a product that looks like this. But if I draw this molecule shown down here, there's no hydrogens on this alpha carbon, but if there were, they would be replaced as well. And then on this alpha carbon, we have 3 hydrogens. We're under basic conditions, and so we're going to replace all 3 of these with a bromine. And so this would be our final product. So keep in mind, under basic conditions, we replace all alpha hydrogens with a halogen, either bromine if we're using Br2, chlorine if we're using Cl2, or iodine if we're using I2. So you might be asking yourself, why does this happen? Why don't we just get a single halogenation under basic conditions, but we actually get polyhalogenation? Well, after the first substitution, and so if we have 3 hydrogens, like in the example I just showed, after that first substitution, we get 1 bromine on there. The hydrogens on the alpha carbon become more acidic. That's because halogens are electron withdrawing. Remember, an electron withdrawing things help stabilize negative charges. And so deprotonating that alpha carbon the second time is even easier than the first time. So keep in mind, under basic conditions, halogenation is faster with the addition of more halogens. So if you look at these 2 compounds down here, we have an alpha carbon with acidic protons we can pull off. And then again here we have an alpha carbon with 2 hydrogens we could pull off. This one is going to react faster because once we pull this proton off, we generate a negative charge. And this is stabilized by the electron withdrawing ability of the halogen. So you might be sitting there thinking, well, what if I don't want polyhalogenation? So if you're in the lab, you only want to add 1 halogen to your molecule. what might you do? Well, you switch from basic conditions to acidic conditions. Under acidic conditions, a single halogenation occurs. So let's take a look at these two molecules shown here. These are both the same molecule. We treat them both with Br2, but we switch from potassium terbutoxide, so a base, to acetic acid, which is an acid. Our outcomes of these reactions are different. Remember, under basic conditions, halogenation, we get polyhalogenation. And so every single alpha hydrogen is substituted with the halogen that we're using, in this case Br2. So bromine substitutes every single hydrogen. But under acidic conditions, we only substitute one of those hydrogens. And so we would get this as our final product. You might be wondering what the heck is HOAC. HOAC is acetic acid, so you might see it written as HOAC, or you might see it flipped around where it's ACOH. You might see it actually drawn out, and so this is the chemical structure, line structure of acetic acid. And then again, I wrote it out here so that you remember what this means. And so this is a weak acid. In this case, we're not using a super strong base, and in this case, we're not using a super strong acid to promote these reactions. So keep that in mind when you're doing halogenation of alpha carbons. So under basic conditions, keep in mind that we generate negative charges and neutral molecules. Under acidic conditions, we generally generate positive charges or neutral molecules. So under basic conditions, we generated an enolate. In acidic conditions, we're going to generate an enol. So let's take a look at the mechanism shown here. Remember, proton transfers are the fastest reaction that can occur. And so we have an oxygen with a lone pair. We have acetic acid over here. The first thing that's going to happen is a proton transfer reaction. And so we protonate our oxygen to get to a molecule that looks like this. And now once we're here, we want to generate our enol. And so think back to the keto enol tautomerization mechanism that I showed before spring break. Once this acetate is generated in this step, it's then going to come back and pull off this alpha hydrogen here, moving these electrons down and moving these electrons up. And so this is going to get us to our enol. So remember that this is called an enol because this is an alcohol, this is an alkene, and so enol. Enols act very similarly to enolates. And so when we draw the reaction arrows from here, they react on the carbon, not the oxygen. And so we need to move these electrons down back to a double bond. And then if we draw out our electrophile, so Br2, this carbon, so we move these electrons down, this carbon then attacks the bromine, and we kick off the other one. What is the result of this? Where our oxygen is still attached to this hydrogen, it's now moved one of its lone pairs down to make a double bond. Has 3 bonds, it gets a positive charge. Our carbon no longer has this double bond because these electrons have now made a bond to the bromine, and then we broke this bromine-bromine bond, and so we have a molecule that looks like this. And then in our last step, we have another proton transfer where we might have another acetate molecule come in, pick off that hydrogen, and give our electrons back to our oxygen, and this would get us to our final neutral organic molecule. So keep in mind, under basic conditions, it was proton transfer followed by SN2 reaction. In acidic conditions, it's proton transfer followed by another proton transfer followed by an SN2 type reaction shown here, and then lastly another proton transfer. So there's several proton transfer steps that occur in this type of mechanism. with the single SN2 elementary step making our carbon-bromine bond. You might be asking yourself, why does under basic conditions we get polyhalogenation, and under acidic conditions we only get monohalogenation? Keep in mind, bromine, chlorine, iodine halogens are electron withdrawing, and so this destabilizes the positive charge that is formed. So after we do a single halogenation, if we were to do another halogenation, keep in mind that the first step was the protonation of the oxygen, and so we get a positive charge. Since the bromine, this means we're lacking electrons. This is sucking more electrons away, and so therefore this is destabilizing instead of, in the case of basic conditions, the halogen is able to stabilize the negative charge. So opposite of basic conditions, when we're under acidic conditions, if we already have a halogen on the alpha carbon, it is going to react slower than if we don't. And so in this case, this will react faster than this. So in conclusion, keep in mind that when we do halogenation of alpha carbons under basic conditions, we get polyhalogenation. So we take every single hydrogen that's on the alpha carbon, in this case there are 3, and we substitute it out with whatever halogen we're using, bromine in this case, and so our product would be the addition of 3 bromines to the alpha carbon. And then under acidic conditions we only get monohalogenation, and so we have acetic acid shown here. That means we replace only one of these alpha hydrogens with a halogen, so our final product from this reaction would be the addition of a single bromine.